Hello, good morning, good afternoon, and good evening to everyone who's joining us for this webinar. I'm Kishan Joshi, the chair of PEL's San Francisco Bay Area chapter, and it gives me immense pleasure to continue bringing more power to 2022 with this webinar. Here's a little bit of history about our chapter. We were the recipients of the 2017 Santa Clara Valley and Region 6 Outstanding Chapter Awards, along with the 2017 PEL's Best Chapter Award. Today's talk is on silicon carbide-based high-density composite electric drivetrain converters by Dr. Dragan Maksimovic, professor at UC Boulder and director of the Colorado Power Electronics Center. Thank you, Dr. Maksimovic, for presenting this talk. I would like to thank our co-sponsors, without whom this wouldn't have been possible. Our IEEE co-sponsors help us spread the word around and help in bringing forward these webinars to the audience. I would like to thank the Dallas PELS chapter, Utah State University PELS chapter, Santa Clara Valley Magnetics chapter, and the Denver PELS chapter for their support. There's a lot of work that goes on in the background in organizing these events and bringing the initiatives to our membership. And I would like to thank the support of each of the members of our team of volunteers and officers from the San Francisco Bay Area chapter of PELS. None of this would have been possible without their support. Do not forget to check out our website for info about current and past talks. Slides and video recordings for a number of talks can be found in the archive section. You can also follow us on Twitter at the link shown below. If you'd like to be in loop on all the great talks, events happening, then IEEE eGrid delivers all of that info down to your inbox for free twice a month. Be sure to register at the link shown here, egrid.biz. Thank you for being here. The PDF slides and the recording of the webinar will be uploaded to the archive section of our website, which you may refer later. Now, a little bit about our speaker today. Dr. Dragan Maksimovic received his BS and MS degrees from the University of Belgrade in Serbia in 1984 and 86 respectively, and his PhD degree from the California Institute of Technology in 1989. Since 1992, he has been with the University of Colorado at Boulder, where he is currently a professor and director of the Colorado Power Electronics Center, COPEC. He has co-authored over 300 papers and 2 textbooks, Fundamentals of Power Electronics and Digital Control of High-Frequency Switched Mode Power Converters. Professor Maksimovic is a fellow of the IEEE and a recipient of the IEEE PELS Modeling and Control Technical Achievement Award. His current research interests include power electronics for renewable energy sources and energy efficiency, digital control of high-frequency switched mode power converters, and high-frequency power conversion using wide bandgap semiconductors. Without further ado, I would like to hand over the stage to Dr. Dragan Maksimovic.
All right, thank you, Kishan. Let me share my screen. All right, hope you can see my screen well. All right, so let's get started. Hello, everyone. So my name is Dragan Maksimovic at the University of Colorado Boulder. And today we'll be talking about power electronics, of course. I'd like to thank Kishan for really having this chapter very active, for advertising this talk and having so many people join us today. So thank you all for coming to the seminar today. We will be talking today about a particular application area for power electronics in the electric vehicle drivetrain or other electrified transportation drivetrains, and then focus on what we are referring to as composite converter architectures, an example of which is going to be applied to the application of the electric drivetrain converter, specifically at 1200 or up to 1200 volts, 125 kilowatt composite converter with the number of topics related to the design and construction of that particular prototype. And then we'll show some more details about the experimental prototype that has fairly high power density and high efficiency. This is the type of slide I include when I give talks to non-power electronics audiences, because we want to emphasize how important we are in all kinds of different applications. And for this audience, I think we can skip that. We know that we have substantial impact on the society and the environment. You know, I've been in power electronics for many years, and early on I was advised to, you know, do programming or do something else, because this power electronics area is not so interesting. It turned out quite the opposite. It's actually probably the most interesting electrical engineering area today, with substantial impact everywhere. And so we are really in an area that has significant, you know, significance, importance, and impact. So we can make progress. A little bit about our Colorado Power Electronics Center. You know, we have 3 faculty in power electronics. Our group was formed by Professor Bob Erickson, also a graduate from Caltech, from the pioneering program of Professor Chuk and Professor Milbrook at Caltech. And I was very happy to join that program in 1992. Recently, we are joined by Professor Luca Corradini from the University of Padua. And we also have Professor Brian Matthias Hodge, who is more in power systems and has complementary interest to us. Our center has a number of industry and agency-sponsored projects, and we are not really focusing on just research. Education is a very important part of our mission. We have 3rd edition of our textbook, very strong undergraduate, MS, and PhD programs, comprehensive power electronics curriculum certificates, and also for those of you who may be interested in looking into some short courses we have on the Coursera platform, you can look up this link at a later time. We are also part of a relatively new center that is focused on electrified transportation, that's led by Utah State University, involves a number of other institutions. It is looking at electrified transportation, not just from the power electronics point of view, but from a broader sense of, you know, transportation systems, adoption, you know, data in both the electric power systems and the transportation system. And the center has more than 50 affiliated institutions that include various industry partners, national labs, departments of transportation, and so on. There are very interesting large-scale demonstration projects, including extreme fast charging and dynamic wireless charging. If you're looking for future speakers for the chapter, I'd be happy to recommend a number of people from Aspire who would be able to provide very interesting talks. All right, so back to the main topic for today. Let's look a little bit into the drivetrain power electronics architectures first. This is a diagram that is trying to give a view of, top-level view of how some of the architectures look like. So on the left-hand side, we have a battery system. On the right-hand side, you have electric drive system. And in some cases, there is a boost converter interfacing the battery system to the electric drive. The reason that boost converter is sometimes used, again, it doesn't have to be there, but it is sometimes used, that it really decouples the design of the battery system from the design of the electric drive system. Gives you another handle for the overall system optimization that can contribute to improvements in overall system level efficiency, size, as well as safety. It also enables dynamic adjustments of the bus voltage in response to variations in operating points. So if you look at the system today, well, I would say maybe recently, as things are moving rather quickly, the battery voltage would be what they would refer to as 400 volt type system. That's fairly standard right now. Whereas this bus voltage can be typically anywhere from the battery voltage to perhaps 800 volts in a system that actually does employ a boost converter. Standard stuff, really, this looks fairly straightforward, right? You have state-of-the-art type designs that are based on, old technology of IGBTs, nothing wrong with that, tens of kilohertz. The drive cycle weighted efficiency for the boost converter here in the middle comes out to be about 95%. And we'll talk about this weighting of the efficiency over a typical drive cycle. Specifically, we'll use this CAFE weighted efficiency that represents a typical range of operating points for an electrified drivetrain. The power density is maybe in the order of 4 to 5 kilowatts per liter, and it's primarily limited by relatively large L and C components in the converter. Right. So before we move on, I'd like to bring up the importance of considering a range of operating points in a system like this. What is shown here is a drive cycle. This particular drive cycle is what is called the USO6, right? You have a vehicle moving from 0 miles per hour, accelerating up to 40 something, then going down, stopping at 0 here. Has a portion of the cycle that spans cruising at relatively high speed, and then some stop and go traffic at the end, and so on. The point of this is that when you examine the operation of the internals of the vehicle over such drive cycle, you find out that the most of the time is actually spent at relatively low power and relatively high step-up ratios for that boost converter in the architecture that does employ a boost converter. And so this is important because it really presents a challenge for any power electronic system to maintain high efficiency over a wide range of operating points that for the most part are actually on the low end, while you have to size the system for example, acceleration performance, and so you have to have significant high power rating at the same time. Unfortunately, at relatively low power levels and relatively high step-up ratios, the boost converter efficiency is fundamentally limited. So when you say 95% efficiency, is that good or bad? Let's look into that a little bit in a little more detail. The way to look at the efficiency, we think is that there is actually a better way to do it, right? We've been in the power electronics area talking about efficiency as being the main quantity that we are looking at. So you say, right, 96%, 97%, is that, how much is this 1% improvement worth? Well, if you just rewrite this a little bit and you say, let's focus on how much output power can we have per unit power loss. This Q, what we call a converter quality, is really just efficiency over 1 minus efficiency. Nothing fundamentally different here. But Q gives you a good way to measure how good your power converter really is. And you can realize quickly that going from, let's say, 98 to 99% efficiency is actually a substantial improvement by a factor of 2, right? So you don't have to spend time discussing whether 0.1 or 1% efficiency is important or not. Q is really a good measure of converter quality. We should try to all use that as a quantity instead of efficiency. It is really showing how small a cooling system can be for a given power processing, and it is directly related to how small a converter can ultimately be. All right, so back to our conventional realization of the boost converter in the drivetrain, the quality factor corresponding to this efficiency would be 18, right? So you'll see as we move forward through various stages of design, we'll get significantly higher numbers for Q. So we'll see we are 2 times, 3 times, 4 times better than that. Those are going to be the language that I will use to show how much better we can do compared to what is conventionally done. All right, what are the trends here? The trends are, of course, to improve Q, right? Improving Q relates directly to making smaller cooling system. And space and weight are at premium in any electrified drivetrain system, so that's important. The other trend is that voltages are moving up because we want to spend less copper to make interconnects. And for example, battery systems are now moving to 800 volts. This is likely going to become a standard. The bus voltages are going to move beyond that, right? You may have bus voltages at 1200 volts for xEV applications. And if you look at the electrified aircraft, the bus voltage may be going into kilovolts range, right? So that's the trend that we are going to see. How to support that trend? Well, of course, you'll say, hey, we have better devices. This is conventional, straightforward, I would say brute force. Nothing wrong with that, but it's a brute force method of saying, let's just use better devices. And the trend, especially in automotive, of replacing IGBTs with silicon carbide is present. Let's try to do that with, let's say, 100 kilowatt 1200 volt silicon carbide based boost example. How much better can we do compared to a standard IGBT based configuration, right? So first of all, we can boost the voltage up, right? That's fine. We can bump up the switching frequency. That is going to result in some reduction in the size of the magnetics. It is not going to reduce the capacitor size. Sorry about that. So if you say, well, I'm going to increase the frequency and reduce the capacitor size, that's generally not true at all, because the RMS currents remain the same, and you really need to use the same quantity of film capacitors for the application. The power devices required here for 1200 volt would be 1700 volt silicon carbide MOSFETs. That's okay. That's available right now. Here is a semiconductor area required. And you can see there is an improvement in efficiency. And more importantly, there is improvement in Q. So you have three times higher Q with a very conventional boost configuration using better devices. Fine. And we can improve the power density along the improvement in Q. Right. So that could be the end of my talk. We just say, right, just use better devices, you're done. But that's not going to be the end of my talk. We're going to look a little bit into just some really, really basic questions. Is there a better boost converter, right? Let's just look into that a little bit. How can anything be better than a boost, right? You have a step up with just two devices, one L and one C. It's super simple. We are used to saying simple is great in power electronics. We want the fewest number of components. All right, let's see how that actually works out. So is there a better boost architecture? Goes back to some basic questions about how boost really works. You have two devices. Q1 is really inverter. It's converting DC to AC power, whereas Q2 is rectified, converting the AC power back to DC. And that amount of power processed by the switches is called indirect power. It is a fundamental mechanism by which boost converter develops voltage gain. And unfortunately, this indirect power processing is really what incurs both DC and AC losses, including switching and magnetic losses. So the basic idea behind the quote mark better boost is to have this indirect power processing done more efficiently, right? So the idea behind what we will be talking about today is to replace the action of these two switches in a boost topology with a more efficient indirect power processor. That leads directly into what we are calling a composite, converter, right? So here is a more efficient indirect power processor. That more efficient indirect power processor is going to be able to step up the voltage while not consuming as much loss as you would have in a standard boost converter, and not exposing the devices, both passives and the semiconductor devices to high stresses in the process. That more efficient indirect power processor is combined with a baby boost, with a small boost that provides the regulation capability, but does not need to step up as much, right? So the combination of these two units, a partial power boost and a more efficient indirect power processor that provides for the step up, gives you a conversion ratio that is a combination of the two and gives you the ability to actually make a more fundamental improvement in the efficiency as opposed to just using better devices. Now, what is going on here? What is this box here? You will see that this box here is called a DCX. And we want to say a little bit more about it before we move on. In general, the composite converter would be an arrangement of dissimilar partial power modules. And specifically to accomplish some of the basic goals behind the composite architecture, we are relying on the efficient indirect power processor in the form of a essentially unregulated stage, right? Regulation is expensive in power electronics. Having a fixed conversion ratio is relatively easy. And that's where the DCX or the float-mark DC transformer comes into play. How can this be realized? Well, there is actually many different ways to do that. Our realization is going to be based on the dual active bridge, but I think you can do it equally well with, for example, LLC or some other resonance structure, right? So let's see how this can accomplish an improvement. So I'm going to take just an example to illustrate the basic idea to start with. Let's suppose we want to convert 400 volts to 800 volts at 100 kilowatts, right? The DCX stage with a 1-to-1 conversion ratio can be designed fairly easily. This, it's been done by many different groups, people and so on, their products and so on. 98% efficiency for a DCX is not unheard of. It's actually fairly easy to do. And you can see that the power is processed through the DCX, whereas the two stages at the output are combining to produce the overall 800 volts at 100 kilowatts, which means that only half of the voltage the modules are exposed to only half of the voltage, whereas the boost at the same time at this particular operating point doesn't do anything. You just pass through. So the boost is in pass through. You have efficient step up with through the DCX stacked with a boost, and the overall system efficiency is realistically possible to have 99%, right? That corresponds to a system Q of 95. Look at this. These are already factors of like 4 times better than what you would have in a conventional boost structure. Overall, the basic ideas behind the composite architecture is that we are reducing component stresses. We have soft switching that enables high efficiency at increased switching frequency. And we are talking about moderate increases in switching frequency, not some exorbitant megahertz or anything like that. We are increasing frequencies from tens of kilohertz to maybe 100 kilohertz. And that's the range where the size of the magnetics can be reduced substantially. The capacitor RMS currents, importantly, are also reduced. You can actually use smaller capacitive components, and major loss mechanisms are really directly addressed. So this idea here is going to be the basis for what we are going to develop as a prototype that I will focus on today. All right, so we'll go now over the details of this particular prototype, 1200 volt, 125 kilowatt silicon carbide based composite converter. I will go through the architecture, partial power converter modules, controls, and some thermal management and packaging. The operating specifications are here. We want to have more than 100 kilowatt power rating, maximum output of 1200 volts. Nominal input is 350 volts, and the ambient is 65 degrees C. We're using silicon carbide MOSFETs from Wolfspeed. The devices that we are going to be using are 900 volt, not 1700 volt, but 900 volt devices in the Wolfspeed HT4000 half-bridge package. Right, the way the system is designed is approached is that we look at this range of operating points corresponding to the drive cycle of interest, and that is then mapped into the bus voltage versus output power operating points. So you have a variety of operating points in that operating space. The more dense operating points correspond to the spending more time at those operating points. So for system optimization, we are considering 64 operating points, and they are arranged in a way that they are emphasizing more those points where we spend more time. Hopefully that makes sense. We are looking for a way of optimizing the converter, excuse me, over a standard drive cycle. right? The composite architecture that we are considering is more complex than the one, basic example that you used as an introduction. It is a two-leg architecture with 4 blocks. Any one of these blocks can be a buck converter, it can be a boost converter, it can be a non-inverting buck boost, and it could be also a DCX, like a dual active bridge. Now, when you look at this problem right here, you can sit down and say, well, in 5 minutes, I'm going to come up with something that makes sense to me, right? And that's fine. But here we are actually looking for what is ultimately possible given the devices available. And so we spend more time looking into the optimization of this architecture and deciding what is actually the best organization of the modules in the composite converter. When you look at that problem, you find out that this becomes intractable very quickly. For each one of these partial power modules, there is a number of things you can change: the number of phases, the number of die per switch position, inductance, core size, number of cores, number of turns, copper thickness. There are at least, there are tens of parameters per architecture that you can optimize over. But there are also many architectures. There's more than 100 unique ways to arrange these converters, each one of which comes with unique conversion properties. So if you want to do an exhaustive search over the parameters, this becomes completely impractical. You don't want to do that, right? And that's just showing how the complex architectures of this type do come with this complexity in the design process. The way we approach this is to have a little bit of a data-driven optimization approach, where each one of these modules here is examined separately. And in the Q versus power density space, we form a relatively simple curve that shows what is the limit. How good of a partial power boost can you have? How good of a partial power buck can you have? And so on. So you perform sweeps over design variables at the partial power module level. Then you capture that into this Pareto front. And once you capture that in the Pareto front, then you say, here is the best trade-off you can do between Q and the power density. Using that, then it becomes relatively straightforward to combine these module-level Pareto fronts to identify the optimum composite architecture. So let's see how that comes out. So here's that operating space with all these different operating points that you have in the V-bus versus output power space. And for the selection of these 4 operating points here, we have families of curves here obtained in the Q versus power density space corresponding to different architectures. Choose boost here, buck here, DCX here, do something else, right? And all of those are examined relatively quickly. This actually doesn't take very long time. It's a fairly simple script to do that. And you see this envelope curve actually is the one that is pointing to the best architecture that we have across these different operating points. That best architecture happens to have this particular configuration: a non-inverting buck boost here, a baby boost here, and then a DCX here, right? So here is the overview of how that prototype system is going to look like. We actually have a 3-phase buck boost converter here. We have a 4-phase boost converter here. And then we have a single DCX present here. You have some details of the performance expected for that system. Ultimately, we are going for a CAFE Q of pretty close to 100. That's going to correspond to overall system efficiency of 99%. Some things to note here is that, and I'm anticipating questions along those lines. You say, all right, you have these million devices here. How can this possibly be better? So we'll get through some of that in a moment. But notice here we have really taken a certain amount of semiconductor area and split that into relatively small die and combine them in a way that is beneficial for not stressing those devices. That's the main point. You have more devices, but overall, collectively, they are stressed less than if you were group them into just two devices in a simple boost. All right, let's see how these parameters actually develop, because there's a lot more detail to cover here. One issue that we're facing is the problems related to magnetics. You know, the classical magnetics were wound transformers and inductors. The scaling that to higher power levels, here we're talking about 100 kilowatt, is difficult primarily because it's difficult to thermally manage those devices. Even with relatively small amount of loss, the 3D structure of traditional, wire wound magnetics is difficult to handle thermally. And that was the main motivation behind looking into planar implementation of the magnetics. And the thermal management enhancement strategies were applied to make it possible to have those planar magnetics be applied at tens of kilowatts level. Those thermal management enhancement strategies include a cold plate, that's a custom aluminum cold plate, thermally conductive ceramic shim between the core and the cold plate, thermal vias embedded into the winding, aluminum bracket placed on top of the I core of the magnetic, and also uniquely inside the winding, we have in the middle of the winding, we have thermal vias, because these internal points within the PCB winding are the points where we actually see the highest temperature rise. Here's a little bit, some photos from the from our lab. This slide, apologize, it's very, very dense. Let me try to explain what's going on here. This is the what you have is a power over power loss. This is a Q for the magnetic components. And on the horizontal axis, you have density, right? And you have different thermal management strategies. In the left corner here, you have passive cooling. And you can see how limited power density can be with passive cooling. As you go towards the right-hand side, you have different thermal management approaches ending up at a point that is really our selected magnetics design that corresponds to these improvements that I just mentioned in the previous slide. And that gives us about 10 times X, 10 times improvement compared to just passive cooling in terms of the overall density. You can see, we can, if there are questions about this, we can come back to this. You can see some of the details in how the planar magnetics are actually enclosed into this structure that provide for efficient cooling. Now, in terms of the control architecture, we have a more complex system, no question about it. I admit that immediately. The more complex system control is done in a hierarchical manner. Each one of these modules has their own classical PWM controller. And then there is a system controller that is directing reference points for each one of these individual modules. At the module level, we are employing online efficiency optimization. Here is an example of how that's done for the baby boost. We are employing the zero voltage switching quasi square wave technique that is giving us the opportunity to zero voltage switch devices across a range of operating points by adjusting the switching frequency and the dead times in response to various operating points. Here are some waveforms that illustrate the operation. So here is a step up of that baby boost of 350 to 500, and opposite, going from then 500 to 350. All of the units, of course, are bidirectional. It's transportation applications. You want to have bidirectional power flow. And you see standard, triangular wave shapes with just sufficient amount of ripple to enable zero voltage switching of the devices. That substantially reduces the switching loss and improves the efficiency of the converter overall. One other thing that I want to point out to these waveforms here and other waveforms you will see a little bit later on, they're relatively clean. These are relatively high power levels in an environment that is pretty tightly packaged together. And having this relatively clean, nice waveforms really implies the system is operating well with high efficiency. The system, again, is complex. I'm going to admit that multiple times today. If you look at the V-bus voltages we need to achieve, anywhere from 200 volts to 1200 volts, with battery voltages anywhere between 200 and 400 volts, our system actually has multiple operating modes. At the low end, it's just a baby boost. Everything else is pass-through, nothing else. It's just a basic operation. Then there is modes 1 and modes 2, where we are employing conversion from either the non-inverting buck boost or the boost to bump up the voltage up, and the DCX is activated. And finally, we have the boost plus the buck boost in the boost stage in this upper end where the step-up ratio is the highest. How do we actually go through these operating modes? That's actually up to the central controller that is directing operation of each one of these individual partial power modules through the operation of the system. Here's an example, right? Going, horizontally here between modes 2 and 1. The bus voltage is maintained, and you don't see any disturbance in it. Whereas as the battery voltage is increased from 200 volts to 400 volts, the boost voltage is going up and down. The buck boost voltage is going down and up, and the combination of the two results in a voltage that doesn't change in the output, right? This is just an illustration of how the system is switching smoothly between the modes as you have various battery voltages while keeping the output voltage here constant at 700 volts. We've done tests with this system moving in all kinds of directions, moving the voltage up and down for a given battery voltage or given different combinations of battery and bus voltages are all handled by the system controller. All right, a little bit about now putting the entire system together. The way the system is arranged is in a sort of a sandwich manner, where on one side we have these, you can see these brackets on top of the planar magnetics. So planar magnetics is on one side of a heatsink. Heatsink provides for liquid cooling, as you would have in a transportation drivetrain. The other side of the heatsink is where you have the silicon carbide modules mounted, and then below that there is a control board that is controlling the FETs. Here is some detail of how the planar magnetics are mounted on the cold plate. This is the heatsink itself, which has this slots where the cores are actually fitting in, and then you have brackets mounted on top of the ferrite cores. So the system as packaged is capable of continuous operation at up to 125 kilowatts with a 65 degrees coolant temperature. Here's the picture of that system. And you can see the dimensions of the system again with the packaging in the 3D way. Here you see the silicon carbide modules at the bottom. And then the top of the board shows the gate drive structure on top of the power devices. I'm not sure whether you can see that. I'm actually holding this system in my hand here. Here's the bottom side of the cold plate, which is where you would insert the planar magnetics, like something like that. And you have a number of these planar magnetic structures inserted. Here's the controller on top of it. So it's all like nicely arranged so that our film capacitors are on the side of the board. And that gives us enough space to actually mount this the heatsink on top of the silicon carbide modules. All right. And some experimental results. We'll go very quickly through this. This is the boost module operation. I already explained it actually is operating with a 0 voltage switching structure. Here are waveforms associated with the DCX. It's a dual active bridge type structure, 0 voltage switching everywhere, very clean waveforms. This is at 50 kilowatts going through DCX with the 98.4% efficiency and a Q of 62. Here's the half power, 26 kilowatts and 98.7% efficiency and a Q of 76. All right, then for the boost module experimental results, all these dots here show the measured efficiency points. Out of all the 64 points over which our system is optimized, we have 55 step-up points and 9 pass-through points. On average, the Q for the baby boost is 133. Here's the buck boost module that is, has 6 step-up down points, 34 pass-through points, and 24 shutdown points. They don't operate at all. This part of the system exhibits on average very, very little loss. You can say, well, is this actually worth adding here? It is. It is allowing us to actually have all these output voltages available with all the battery voltages available while consuming overall very little power and very little room in the process. For this unit here, the Q on average is actually more than 600. And then finally, the dual active bridge-based DCX. For the most part, it operates at the nominal 1-to-1 ratio. At the edges, it has to go a little bit away from the nominal 1-to-1 ratio, and those points do have a little bit lesser efficiency, but overall, the losses on the unit are still very low, and the Q on average is high. So here's the complete system. You have over this corporate average fuel economy drive cycle, the average power, the average loss, and the Q for the individual sub-modules and for the overall system. And this is based on experimental results. The overall system Q is 98.6. That corresponds to the overall system drive cycle weighted efficiency of 99%. All right, let's compare the composite to the silicon carbide based conventional boost. Same voltage, right? Here we have 60 kilohertz for the conventional boost. We can bump that frequency up to between 100 and 350 kilohertz. And this increase in frequency here is well justified by the reduction in the size of the magnetic components. Standard boost, wire wound magnetics. Here we have entirely planar magnetics. One of the, I would say, unique system examples where the planar magnetics approach is extended to pretty significant power levels. That's what we have here. In both cases, we have film capacitors, but since the RMS currents in the capacitors are so much smaller, we have 4 times smaller capacitor volume. The power devices here are 1700 volt silicon carbide. They're available. Here we have 900 volt silicon carbide. And you can again say, oh, well, you have so many more devices. The area, the total area of the devices in our system is actually smaller than the total area of the devices you would have in a classical boost. I mean, say here is approximately the same. It's actually a little less. We have another 50% improvement in Q. The average efficiency is 99%, and the power density is another 2 times higher compared to what you would obtain with the conventional silicon carbide based solution. The final item I want to address here is what we've heard many times when we talk to various people about this approach. Again, you have many devices. Forget about it. You're not going to do that. Your reliability is horrendous. Well, let's actually look at that. So I have to admit this is going to be just calculation based, but it's not completely empty. The calculated mean time to failure for this system here, conventional boost with silicon carbide, this is what you would do in a straightforward manner, is actually 3 times lower than the calculated MTTF for our system. Even though we have a larger number of devices, those devices are stressed less, right? The calculation of the MTTF follows standard industry practices. We have included the failure mechanisms for silicon carbide MOSFETs, for gate driver ICs. Yes, we have more gate drivers, true, but again, they're driving smaller die and they are rated at lower current levels. That actually does matter. And we have included the MTTF contributions for capacitors. So given all that, the actual calculation gives us an improvement in MTTF, not a worse MTTF, even though we do have more components in our system. All right, so in conclusion, I'm going to wrap things up here and hope we get some questions on this. The power electronics is such a phenomenal area. You know, you can invent new things. And you know, we're not, of course, saying this is the only way to do it, but really just being happy about how the area can provide for innovations in many different directions. It is not sufficient to just have better devices. It is good to think about how to make best use of those devices. And in some cases, you may end up with a conclusion that it's actually best to use silicon MOSFETs. And in some other cases, it may be silicon carbide MOSFETs, whatever. We want to be open to those opportunities and make best use of the available devices through topologies and architectures that we come up with. This particular prototype was a pretty significant effort in terms of design optimization and control techniques. We also have some, I would say, innovations in the packaging and system integration techniques, and really showing how power and voltage scaling can be done using composite architectures with planar magnetics is I think, interesting. And last but not least, I would say, yeah, simple can be great in maybe 90% of cases, but there are cases where you want to open a little bit into considering the possibility of doing a little bit more complex architectures that can provide for some fundamental improvements. That's not always the case. I'm not going to advocate many devices in many cases, but we want to be open to that as an option. Finally, I want to give credit to the team. This project was done with the principal investigator being Bob Erickson, and our two PhD students. I cannot really give more credit to anyone here than the PhD students, Yucheng Gao and Vivek, who have done phenomenal work in all aspects of this design. And really, 90% of what I was talking about is their work. I also want to highlight phenomenal collaboration we had with the Toyota Research Institute, who contributed greatly to the heatsink design and the overall thermal management study. And Enrel and Barry Meder and Mariko Shirazi at University of Alaska Fairbanks, who helped us with the controller hardware in a loop development of the control, some initial development of the control, and then finally devices that are coming from Wolfspeed 3. This project was an ARPA-E circuits project directed by Dr. Isaac Kizriali. Right, there's references here. You know, you can of course look into more details in papers. And I'd like to thank you for your attention and look forward to your questions right now.
Thank you, Dr. Maximovich, for a very exciting talk. I'm sure the audience will concur with me that this webinar has been very illuminating. We'll now go to the question and answer part of the webinar. I would like to remind the audience to post their questions in the Q&A box, and we can go with that. All right, so let me get started off with the first question. So by how much does the improvement in Q factor of the power converter correlate to the improvements in the range of EVs?
Right, okay, great question. The improvement in Q factor of the power converter, of course, does improve the range, but it doesn't improve much, right? You know, it is really, the improvement in range is directly proportional to efficiency, right? So if you go from 95 to 98, you're going to have 3% improvement in efficiency, and you're going to have 3% improvement in range. And that looks like, hey, you know, this whole thing is not worth it. It is worth it from the point of view of size of the unit, right? So you can put the, you know, you can spend less of the real estate on the power converter. That's the major improvement, not so much the range of the EV.
Okay, thank you. Why not use a dual active bridge or LLC all the time? Is it because of the wide VIN?
Right, right. So the, you know, maybe I go back to one of these, see if I can, sorry, I'm gonna shuffle through this now. Oh, here, right. So you have wide range of battery voltage. You have also wide range of bus voltage that you want to achieve. You could technically operate this DCX all the time, but that would eliminate, you know, the bottom part of the operating points that you are trying to reach. Another reason we don't want to operate converters that are not contributed to the conversion is that we want to save the power. You know, you don't want to operate the units that are not needed at any particular point in time.
Okay, all right. What is the soft switching scheme used in this design?
The soft switching scheme used in the design is, well, here's an illustration. So for the standard units, like the baby boost or the baby buck boost, the soft switching scheme is called zero voltage switching quasi square wave. It's really no different from operating the converter in a standard pulse width modulated mode, except you let the ripple current in the inductive component be large enough so that you get just enough of the negative current available to swing the voltage in a zero voltage switching manner at the transition. This is very old stuff. It actually comes from the time when I was doing my PhD at Caltech. And you know, I'm happy to see this stuff actually applied in all kinds of different ways. So this is fairly simple. For the dual active bridge, we rely on the zero voltage switching properties of that unit itself.
Okay, thank you. So what is the isolation voltage for these modules? Is it 5 kilovolts or 1.5 kilovolts? How does this affect the sizing of the magnetics?
Right. So for the magnetics, right, the transformer, like one of these units, this is actually one of these DCX transformers, the planar things. We have a few kilovolts of isolation between primary and secondary. The overall system is not isolated. It shares the common ground between the battery and the electric drive system. So the system is not isolated. The DCX has a transformer isolation.
Okay, yeah. Generally, converter processing more percentage of indirect power has lower efficiency. With indirect power theory, how would you justify the high efficiency of DAP or more generally DCX, which processes 100% indirect power?
Right. Okay. Well, that's a fantastic question. That gets us back into some of these basics about the indirect power and direct power. For a given step-up ratio, the indirect power, you cannot reduce the amount of indirect power. There is a limit to how low indirect power can be. Boost converter and our converter are going to process the exact same amount of indirect power. We are not reducing the amount of indirect power processed. We are processing indirect power more efficiently. So if you need to step up with a boost from X voltage to 5X voltage, the indirect power processed is 4 of 5, right? And that's pretty significant. And it's done very inefficiently because both devices are exposed to high voltage stress. And both, you know, you don't necessarily have zero voltage switching or all these other things, right? You're exposing components to high stresses. In our system, that 4 over 5 of the power is processed much more efficiently through the DCX unit that is not required to perform regulation.
Okay, all right, thank you. So the next question is, will the power density further increase if the silicon carbide module could be customized? Any estimation of the improvement?
Right. Okay, great. You know, I'm not sure I can answer that question. It's possible, right? You know, you can see these, you know, let me see, where is this? Yeah, these are actually fairly large packages. And this is about three years old project. And this was kind of a starting point. This is what we have available at the time. So it was a constraint that actually has driven some of the arrangements of the components. If we were to start from scratch and look for different packages, I think that would be yet another dimension to explore. It's really hard for me to tell how much improvement would that lead to in terms of power density. The rearrangement could be done in a way that I'm sure there is a potential for some improvement in power density. I don't think it's huge, right? You know, we may trim out another 10, 20% of size, you know,
sure.
My guess.
Thank you. So the next question is, how do you limit the EMI, EMC in the circuit and protect false turn-ons in the converters?
Right. Okay. So the EMI thing here has been challenging. Of course, we know how to do layout of our control boards and the power stage board, and we know how to minimize loops, and you know we know how to do this stuff, right? And even then, stacking these things on top of each other did present some challenges. We had a number of iterations of the prototype with, you know, false triggering on or even the microcontrollers being affected by the EMI, and really going through those iterations and learning, you know, through the process is really what led into the system that is shown here, that is capable of robustly operating over all these, you know, different operating points. But surely a more thorough, more fundamental work related to EMI is, I think, one of the things that could follow up on this.
Okay, all right. There are a couple of questions on the EV range impact. So firstly, what is the biggest bottleneck to the EV range today? The power density, if greatly reduced, how will the EV range be improved considering both the same battery setup, efficiency, and volume weight reduction?
Right, the range is determined by the size of the battery, right? I mean, you know, it has nothing, well, it has a little bit to do with power electronics, but not really that much. So EV range, you know, that's, you know, what cells you have available. We do have some impact in terms of how we do battery management. The powertrain, power electronics does make a difference, but that's not huge, right? You know, again, these are percentages here. Let me re-emphasize that the size of power electronics is what actually matters here more than the impact on the range. I'm not sure if there was something else related to maybe I missed a portion of that question.
Yeah, so the other part was, let me just quickly go over that. The power density, if greatly reduced, how will the EV range be improved considering both the same battery setup, efficiency, and volume weight reduction?
How would, I mean, you know, I know everyone is concerned about EV range, right? But EV range is really just the battery size. You know, it's not, you know, I don't think this particular work is having a huge impact on the range itself. Indirectly, perhaps it is, right? If you have less, you know, less space spent on power electronics, you have more space available for the battery, so you can improve the range. I guess, you know, maybe you can answer it that way.
Right. Okay. Sure. So moving on to the next question, are there any specific subblocks or components where losses are concentrated and to be looked into?
Yeah, the biggest thermal challenge we have was not on the semiconductor devices. It really was on the planar magnetics. And I tried to mention a little bit of that earlier. This planar magnetics thing it's really easy to do at low power levels. And that's great. You know, we do that routinely, right? You know, a few 100 watts or kilowatts or anything like that. You try to make a planar magnetics for 10 kilowatt. It's really difficult to do that unless there is some way of dealing with the heat generated on the windings. You know, this is printed circuit board windings, right? And you can see this stuff of having this centrally located thermal vias. That's like a last ditch effort to bring the thermal the temperature rise on the winding down to the acceptable level. So the thermal management strategy around planar magnetics was really what made it possible to scale the planar magnetics to such high power levels.
Okay, all right. So the next question is, have you investigated switched capacitor converter for the direct conversion unit?
No. So in this project here, we stuck with the dual active bridge. But yes, I do really like hybrid-based DCXs. We have tons of that. You know, if you invite me to talk about it some other time, I'd be happy to do that. It might be possible to do that. You know, just eliminate the transformer in the DCX entirely. I think that would be worth looking into. Okay, all right.
I guess, yeah, the next question is, could this converter be built by GaN HEMT? Any possible benefits by higher operating frequency of the GaN device?
Well, as far as frequency is concerned, I think this is a really good spot. You know, if 100, 200 or so kilohertz, that's really where you get the benefit of reducing the size of magnetics. Increasing that frequency up in this particular system would be counterproductive. So can we switch at higher frequency? Well, I guess we could. We shouldn't do that. In this particular system, I think that actually would be counterproductive.
Okay. So the next question is, it seems that flying capacitor multi-level converter can also use low voltage rated silicon carbide MOSFETs. Besides the flying capacitor converter having a modular design, what is the biggest advantage of the composite architecture over the other type?
Right, yeah. Flying capacitor multi-level converter is a beautiful topology. I personally really like it. In this particular case, that topology would not work really well. And the reason it wouldn't work very well is that for a number of reasons. One is, first of all, yes, you could split the voltage across these multiple devices. That's great. It would be very difficult to actually have soft switching on those devices. And second, worse perhaps, is that you would need to employ capacitors of substantially higher volume because the RMS currents through the capacitors in the flying capacitor multi-level topology are significant.
Okay. Okay, so thank you. The next question is, are there any standards used to determine the required filter size for powertrains?
Are there standards required to determine filter size for powertrains? Well, I'm not sure actually. So this is this block, going back maybe to the very beginning. If you look at this stuff here, right? You have a battery system, you have a boost converter. Again, let me just emphasize, there are also systems that just nix this boost converter entirely. You just connect directly battery to the electric drivetrain. That's fine. But if you do have a boost converter here, then you follow that with the inverter. These things are internally tied together. If you look at some of the commercial units that follow this particular architecture, this stuff here is in one box. You don't really, there is no you don't see the interface between these two units. And then with respect to the battery, is there a standard for interface here? I'm not actually sure. Maybe someone in the audience knows better than me. Yeah, there are EMI standards related to this automotive stuff, of course, but the filtering on the input side here, I'm not sure what the standard is. Yeah.
Sure. So for the zero voltage switching at such high power, are the switching losses still significant considering that the conduction losses are increased?
The conduction losses are increased a little bit. The switching losses are very low. We had test structures to calibrate our switching loss models. There are residual switching losses because we are turning the devices off at non-zero current. Those are second order effects. They're relatively small. And then silicon carbide actually does switch, turns off quickly. So that's nice. So Yeah, the overall trade-off is heavily in favor of what we have done here. So reducing the switching loss to as much as possible with a relatively slight penalty in terms of conduction loss.
Okay, thank you. So there are two questions on the planar magnetics. So firstly, how much heat flux were the planar magnetic windings and cores operating with? And is this concern the limiting factor for increasing the switching frequency even further?
Yeah, it is. Well, so to answer the second question, yes, the ferrite-based planar magnetics at this power level, it would be extremely difficult, if I would say most likely counterproductive, to increase the frequency further. So we are at the range of frequencies of 100 to maybe 300 kilohertz, where we have the I would say the best design for the planar magnetics at these power levels. And the heat flux, it's I would really maybe invite you to take a look at one of the publications we have in particular. Let's see which one. Very recent one. Oh yeah, this one. Yu Cheng is the first author. The modeling and design of high power high current triple planar inductors. This actually goes to extensive detail about the thermal management of the high power planar magnetics.
Okay, so we'll go over one last question, Dr. Maximovich, and then close. So how does this big Q impact the dynamics of the overall output during load transients?
Right. So there's a whole story here that's not even touched related to the control in terms of dynamic response. So again, we have this hierarchical control structure where you have local controllers for individual units, and then there is supervisory controller that is directing the reference points for these local controllers. So dynamics of the system is actually fairly, again, it's complex. What can I say? This system actually does involve a number of dynamic converter blocks, and dynamics of the system is complicated, but it can be worked out. If you say, well, the complexity is control, I don't buy that as being a problem, because we can do control really well on complex power electronic systems. That's fine. In terms of dynamic response, the system where this is operating in has dynamics that are not terribly demanding. We're not talking about a VRM for microprocessor. We are talking here about supplying power to an electric drive system. And so the dynamics involved are not terribly fast, right? The way you're accelerating, decelerating, and so on, it exposes this converter to dynamics on the order of tens of or hundreds of milliseconds, right? So it's not a terribly fast system.
Right. Okay. Yeah, thank you so much. I think that concludes our Q&A session. I know we couldn't get to all the question and answers, but we are already 10 minutes over. I want to thank you, Dr. Dragan Maximovich, for such a wonderful talk. We had a really good audience participation with lots of questions, and you answered so many of the questions very comprehensively. Thank you for your time. And I want to thank all the audience for joining in on this webinar. And I want to thank our IEEE co-sponsors for helping conduct this webinar.
Yeah, thank you again for organizing this seminar. It's been wonderful to have so many really people come to the seminar. Thank you all for coming, and thank you all for the questions. If you want to follow up with questions, it's very easy to find me. Shoot an email to me. I'll be happy to follow up with you on that.
Thank you. And just a reminder, the recording and the PDF slides for this webinar will be uploaded in the archive section of our website. So please keep a lookout on that. Thank you all. Have a good day, good evening.
Thanks.